All right. Hello, everyone, and welcome back to Solid State Physics in a Nutshell, brought to you by the Physics Department at the Colorado School of Mines. My name's Eric.
And I'm Nicole.
Today we want to develop a common vocabulary that we can use throughout the course to talk about crystals and their microscopic structure.
Just to be clear, everyone, when Eric says crystals, most people tend to think of macroscopic structures with clearly defined facets, like diamond, table salt, and snowflakes. While these are indeed crystals, it turns out even something like aluminum is composed of crystals, which may not be obvious now, but by the end of the video it should be.
One thing to notice is the different bonding that exists in each of these examples. We have examples of covalent, ionic, hydrogen, and metallic bonding, indicating that crystals form regardless of the bonding present. Indeed, most solids can be formed as a crystal.
Since we deal a lot with crystals in this class, it'd be a good idea to be clearer about our definition of a crystal. Imagine holding a diamond in your hand and zooming in on one of these facets. As you get to the individual atom scale, one would see a periodic arrangement of atoms that have translational symmetry.
When we say translational symmetry, imagine a vector t built out of three vectors. If we took some function f of r and translated r by this vector t, we should get to our original f of r. Physically, we can imagine this function as the position of our atoms or the electron density.
Given that crystals have this sort of symmetry, there's going to be some repeat unit that, when repeated through translation, creates the entire crystal. We call this the unit cell, and it describes the chemistry and symmetry of the crystal. But how are we going to separate them?
We'll do so through two terms, called the lattice and the basis. We associate the overall symmetry of the crystal with a set of points called the lattice, while the chemistry of the crystal is described by the basis. For the moment, let's ignore the fact that we have atoms, and imagine one point in space. Using the vector t that we developed before, we can populate space with a framework of points.
Where this point is 1a1, 0a2, 2a1, 0a2, and so on and so on.
Right.
Looking at this lattice we've built, it seems like I can choose these vectors for a1 and a2 instead and still be able to recreate all space. So the original a1 and a2 we chose aren't unique?
No, they're not. Likewise, we can choose any origin we want. All the lattice has to do is satisfy the constraint that when tiled, it creates the crystal. Since both of our selections do that, they're both perfectly valid.
Now that we have a good mathematical framework to describe the symmetry, we need to bring in some atoms. How we decorate each lattice point is given by the basis.
To be clear, one should remember that the basis is not the same as basis vectors that are used in quantum.
Maybe an example will help clear this up. Imagine a crystal of magnesium and oxygen atoms in the following configuration. Let's pick our origin to be at this magnesium atom. Upon inspection, I notice the square is our smallest repeating unit, with vectors a1 and a2 as so.
Using translational symmetry, we'll populate our crystal with some lattice points. Now looking at our points and the relative positions of our atoms, we can see that there's a magnesium atom at our origin and an oxygen atom at a1 equals a half and a2 equals a half.
But Eric, there are also magnesium atoms here, here, and here. Why don't we include those in our basis?
Those atoms belong to the origin of the other unit cells and will simply get created through translation.
Okay, I see that now. What if instead of choosing my lattice vectors to form a square, I choose them to form a rectangular cell?
Yeah, so it turns out that just like the lattice vectors, there's not a unique basis for the crystal. Indeed, it depends on what lattice vectors you choose for your crystal. In this example, with the rectangular lattice, our new basis would be this instead, with the coordinates now relative to the new a1 and a2.
So the lattice turns out to be pretty important. Let's look back at it. Typically in solid state, we either talk about the primitive or conventional lattice. The primitive lattice is the smallest area or volume cell that still spans free space upon translation. So if you had a lattice as so, you can imagine choosing vectors a1 and a2, but you could also choose a1 and a2 like so as a different but equally valid primitive cell.
Because we can choose any primitive cell, one should be careful. The whole point of the lattice is to reflect the highest symmetry of the system. So one could choose this oblique lattice, but it wouldn't make any sense compared to choosing the square.
In 2D, we have a set of special lattice types called the Bravais lattices that represent the unique lattices. These are the square, hexagonal, oblique, rhombic, and rectangular cells. While the primitive cell is fairly simple, sometimes we need something to better describe the full symmetry of the crystal.
Exactly, and we achieve this through centering. Take the rhombic cell as an example. While this primitive cell works to span real space, we often use the centered rectangular cell, named so for the lattice point at the center of the cell. While this is not the primitive cell, the 90-degree corners makes the 180-degree rotational symmetry of the lattice more obvious.
So this would be an example of a conventional cell. Not only does it better reflect the symmetry, but frankly, rectangles are easier to work with as well.
Exactly. Could we do the centering to the other 2D Bravais lattices, like the square?
No.
Why?
Well, it doesn't look like we'd get any more information about the lattice symmetry. For instance, if I made a centered square lattice, I could just as easily choose new A1 and A2 vectors and get a square again.
Absolutely. As in 2D, we also have Bravais lattices in 3D, as given in this table here. Although we just call it centering in 2D, in 3D we actually have different types of centering. There's a base centering, face centering, and body centering, which are shown here. It'd be good to get familiar with this table and know examples of each.
And with that, we've wrapped up our core discussion of the microscopic structure in crystals. But it would be good to relate the microscopic to the macroscopic structure of materials.
Earlier, Nicole, you said that most people think of facets when they think of crystals. When you see facets in a crystal, what you're really seeing is the exposed planes of the unit cell, all aligned in the same direction. Take pyrite, for example, which has a cubic unit cell. Lo and behold, it also looks like a cube in its macroscopic form.
So far, we focused on single crystals, but in practice, many metals, such as aluminum, are composed of many small crystals in different orientations. So aluminum, while it doesn't have facets, does indeed have a microscopic crystal structure.
So it looks like it's time to do a recap of today's video. In short, we found crystals exist across a variety of structures and bonding types. We broke this microscopic structure into a description of the crystal's translational symmetry, called the lattice, and a description of the crystal chemistry, or the basis.
We also looked at different types of lattices, including the primitive and conventional cells. While both recreate the crystal under translation, often the conventional cell is easier to work with, as in the case of the rhombohedral versus centered rectangular cell example.
In closing, here are a few things to think about on your own.
Earlier I talked about how it doesn't make sense to talk about a centered square lattice. Why wouldn't it make sense to have a base-centered tetragonal cell?
To give you some further practice, here's a set of wallpaper motifs. Can you find lattice points and vectors for each of these? Well, that about does it for today. Next time, we're going to look at visualizing crystal structures in a more robust way. Thanks for watching Solid State Physics in a Nutshell. See you next time.